Okay, good morning. So let us continue our learning. So we have started learning about MRAM technology. Yesterday I discussed about how do we write information in MRAM. So writing is basically switching the magnetization of the free layer. So if we switch the magnetization of the free layer parallel to the, maybe we will do a recap of what we learned today, yesterday. The reference layer magnetization is always fixed in one particular direction. So writing 1 means making the free layer magnetization to be anti-parallel to the reference layer. Writing 0 means making the magnetization of the free layer to be parallel to the direction of the magnetization of the reference layer. Okay. So this is basically writing. So since we are switching the magnetization, we also use the terminology switching to represent writing information. So I taught you a few techniques to achieve switching. The first concept that we learned is using magnetic fields generated by current carrying wires. Okay. So in this particular case, we have two wires. Let us say there is one current carrying wire this way, let us call it a bit line. Then there is another wire, let us call it a right line. So another current carrying wire. The MTJ that you want to switch is somewhere here in between the two wires. Okay. Let us say this is at the bottom. Let us say this is at the top, the MTJ is in between these two. So when you send current through the two wires, you are producing orthogonal magnetic fields. Okay, so these two fields are in an angle of 90 degree with respect to each other. So one of the, let us say one field is parallel to the EZ direction, let us call it EZ H. Okay. So what this field does is, I mean, in the absence of any magnetic field, we have this kind of energy landscape. Okay, so we have EB, which is KUV. So we have two EZ directions. When you apply magnetic field in the EZ direction, it changes the energy landscape a bit. So the energy barrier is reduced now. Okay, so when you apply magnetic field in the hard direction, the hard direction magnetic field reduces the height of the energy barrier, is smaller now. Okay, so just one magnetic field cannot switch because these magnetic fields are not large enough to change the energy barrier landscape completely. Okay. So by using these two magnetic field together, then we can exceed the energy barrier and we can switch the magnetization. Okay. So this is the technique used to selectively switch MRAM. Okay. So only the MRAM, the MTJ cell which is in this intersection will be switched. All the other MTJs along this line or along this line, they will not be switched, okay, because they feel either this kind of energy landscape change or they only see this kind of energy landscape change. So there is still some energy barrier. So none of these MRAM MTJs will not switch, none of these will switch. only this particular MTJ will switch. Okay. So, this is one concept that we learnt yesterday. Then the second concept we learned yesterday is STT switching, spin transfer torque based switching. So, to understand this one, we learned, we recapped the concept of angular momentum transfer. So, spin, magnetization, all are angular momentum. Okay, so, there can be angular momentum transfer between spin and magnetization. The second concept that we learned when we talk about spin transfer torque is spin polarization. So, for example, if you take a copper wire, you send electrons, almost equal number of spin up or spin down electrons will come out. Okay. So, there is no difference in the number of spin up or spin down electrons when you send a stream of electrons through copper. Okay. On the other hand, if you send a stream of electrons through a ferromagnetic materials magnetized in one particular direction. So, in this case, the number of electrons that have magnetic moment in the same direction as magnetization will come out more in number, and the spins with opposite magnetic moment will come out fewer in number. Okay. So, this aspect is called spin polarization, and we are using this property to switch the MTJ. Okay. So, if you have a reference layer like this, spacer, then free layer which has anti-parallel magnetization, and let us say you send a stream of electrons through this layer, and if these electrons are majority in number, they will exert a torque on this magnetization. So, finally, these two will become parallel. Okay. So, we call it AP to P, anti-parallel to parallel switching. Okay. So, remember that torque will happen only when there is a component perpendicular to the magnetization. Okay. So, either the spin should have some component along this direction which is perpendicular to the magnetization, or if spin is like this, then this magnetization should have some component. For example, if the magnetization is like this, then there will be a horizontal component which is perpendicular to this spin. Okay. So, torque will be non-zero only when the spin, a component of spin or magnetization are perpendicular. So, I was always showing spin up, spin down electrons going this way, and this magnetization also is perfectly parallel. Okay. So, you may wonder how it can switch. So, when these two are completely parallel, there cannot be torque, there will be no switching. So, what happens when you operate MRAM, for example, first of all you are operating at room temperature. So, there will be thermal fluctuations. Secondly, you are also sending current, there will be some joule heating. So, maybe you even go from room temperature to slightly higher temperature, let us say 80 degrees Celsius or something like that. Okay. So, this temperature will make the magnetization to fluctuate. Okay. So, this free layer magnetization is not completely parallel to the spin magnetic moment because of the fluctuation. So, it may be rotating or something like that. Okay. So, at some point of time there will be some horizontal component. So, on this component the spin magnetic moment will act, then you will have switching. Okay. So, this point I missed yesterday. Okay. So, this is one way of switching. and if you want to switch from parallel to anti-parallel, you just reverse the direction. Okay, so, the electrons that get reflected from this interface go and switch the magnetization from parallel to anti-parallel. That is second concept that we learnt. The third concept which we learnt yesterday is spin orbit torque MRAM. So, in the case of spin orbit torque, we are looking at let us say we have a nucleus, electrons are going around. So, from the electrons perspective, it will appear that the nucleus is going around the electron. So, there will be a magnetic field. Okay. So, that magnetic field and the spin interact. Okay. So, that gives rise to the spin orbit coupling, and because of that we have the spin Hall effect. That means, if you have a heavy metal layer and you send a current through the heavy metal layer, okay, one type of spin will come up, then in the bottom side you will have the opposite sign. Okay. So, we can use these spins. Let us say we have another ferromagnetic layer on top. So, we can use these spins to exert torque on the magnetization of the ferromagnetic layer and switch MRAM, switch the free layer. Okay. So, in STT MRAM typically the heavy metal is at the bottom, then free layer is at the bottom, we have magnesium oxide, reference layer is at the top. And we need 3 terminals. Okay. So, we have one terminal, I mean 2 terminals for sending the writing current. Okay. Then for reading we use another path. So, we have a third terminal through which we send current and we read information. Okay. So, this is the reading path. And this is the writing part. Okay, so, because of this we have some advantage. I told you that writing current is larger than the reading current. So, in the case of SOT MRAM, so we are sending the larger current through the heavy metal. So, it does not go through the magnesium oxide. So, it does not break down the tunneling barrier. So, in the case of STT MRAM, tunnel barrier breakdown TBBD is a problem. It is a problem in STT MRAM, but it is not a problem in SOT MRAM. Okay. So, these are some concepts that we learned yesterday. With this recap, let us move on to today's topic, which is about what are the research work that have happened in the aspect of storing information. Okay. So, we finished writing, we will discuss about storing today. Okay. So, as far as storage is concerned, you know that the energy barrier is the one that helps to retain the information, and the energy barrier comes from the magnetic anisotropy. Okay. So, you learned that KUV is the energy barrier that helps to retain the information. So, this Ku can come from materials. For example, you take iron platinum, L10 iron platinum. So, this material has anisotropy of the order of 10 power 7 earth per cc. It comes from the magnetocrystalline anisotropy. So, it is a material property. On the other hand, if you take say cobalt platinum multilayers, so here the anisotropy is coming from the interfaces. Okay. So, any anisotropy is okay. So, as long as there is an anisotropy and the material has certain volume. So, in the case of MRAM, this volume is basically the cylinder's volume. So, we are having devices in the form of cylinder. So, you know the diameter, you know the thickness, you can calculate the volume. So, this volume multiplied by Ku gives rise to the anisotropy energy, and that is what helps us to store the information. Okay, so, this one we have seen many times. So, based on how do we store information, we have two types. One is called in plane MRAM and another is called perpendicular MRAM. So, if you remember when I taught you the magnetic recording, I told you that there is something called longitudinal magnetic recording technology, where the magnetization in the recording media is parallel to the disc. Then we did not learn the perpendicular recording technology, but in the perpendicular recording technology I told you that the magnetization is perpendicular. Okay, so, we use almost similar concepts. So, in hard disk technology, this longitudinal recording technology was used from 1956 to almost 50 years it was used. Then somewhere in 2025, the perpendicular 2005, this perpendicular recording technology came into picture. So, in a similar fashion, in MRAM also, in plane MRAM was the oldest technology, and perpendicular recording technology is the newest technology. So, you may wonder why we did not start with perpendicular MRAM right away. Okay. So, we know that perpendicular recording technology is better. So, we should know that perpendicular MRAM will be better. Why we did not start right away with the perpendicular MRAM, why did we do this? So, you will learn that today. Okay, let us first start with in plane MRAM. Okay, the first reason is like why we start with in plane MRAM in the beginning at all. Why do not we start right away with perpendicular MRAM? It is because of the reason which I have told you many times before. The hard disk technology is the pioneer of spintronics technology. So, almost everything except spin orbit torque comes from the hard disk technology. Okay. Until the spin transfer torque, everything comes from the hard disk technology. Okay. So, in hard disk technology we use readers. Okay. So, we learnt about TMR readers, tunneling magnetoresistance readers, which looks exactly like this. Okay. So, you have a pinning layer. So, this magnetization is pinned at certain angle, and you have a free layer whose magnetization is perpendicular to this one, and we are using the magnetization direction of the free layer to read information, right. So, when people were working on this concept, they thought, okay, we should try to make memory out of the same TMR or GMR devices that we are working on. So, that is the reason why the MRAMs of the earlier days were of in plane types. Okay. So, it basically is like a spin off. So, you do this one, but you also try to use the same sensor design for MRAM application. So, that is one reason why the most of the early generation MRAMs were of in plane types. Okay, so, here we are talking about storing. So, we can store the magnetization in at least two different ways. Okay, one is like the two layers are parallel to each other. So, resistance will be low. So, if you send a current through the device, you will find that the voltage is low. Okay, you can call this as 0. You can have another state where the two magnetization are parallel. So, if you send current through this device, you will find high resistance. So, you will see a large voltage, you can call that as 1. Okay. So, these are the two states of storing information. So, you may argue that we can have like the two layers orthogonal, all those things. You can have maybe intermediate states, but it is useless. Okay. We do not have that much change in the TMR between these two states. So, people are happy with the just two states as of now. Okay, so, as I mentioned yesterday, the reference layer has so many names. Okay. So, I may use fixed layer, sometime I may use polarizing layer, pinned layer, reference layer, hard layer, all these layers refer to this layer whose magnetization direction is always fixed. Okay. So, this layer is called with so many names, and the free layer whose magnetization can be changed to be parallel or anti-parallel has a few names like this. Okay, so, I mean the key point here is that in plane MRAM, the magnetization is parallel to wafer. Let us say you have a 12-inch wafer. Okay, so, the wafer will look like this, I mean circle 12-inch. The magnetization is parallel to the wafer. So, that is the in plane MRAM. Okay, so, in plane MRAM usually uses soft magnetic materials like cobalt, iron, boron. Okay, the reason being, as I mentioned, this is an extension of read sensor projects from hard disk industry. So, they have been using this cobalt and boron. So, they just stick to the materials used for read sensor. And the second reason why we use the softer magnetic materials was because at that point of time, let us say people are doing this research in 2000 or earlier, we do not have the concept of using STT to switch magnetization. So, we were relying on the magnetic field assisted switching. Okay, we learnt about magnetic field assisted switching. So, we relied on this switching method. So, if you want to use high anisotropy materials, then the current you require to switch was a problem. Okay. So, because of these two reasons, the in plane MRAM community, they always used cobalt and boron. So, in this particular technology, as I mentioned before, we pin the magnetization direction of the reference layer with a pinning layer, which is then antiferromagnetic material like iridium, manganese, for example. Okay, so, that is the second point. The third point, yes, we use exchange bias. So, I gave you this recipe. So, we use a magnetic field and anneal the ferromagnetic antiferromagnetic stack. Okay. So, this induces one easy direction. Okay. So, this is the third step. And the fourth reason is like in 2000, people were not aggressively looking for small MRAMs. So, for large size MRAMs, cobalt and boron was okay, no problem. Okay. So, because of all these reasons, people used materials like cobalt and boron. Okay. So, this you have already learnt. So, we are using the interface anisotropy, which is also called unidirectional anisotropy, to pin the magnetization direction of the reference layer. So, we have iridium manganese as the antiferromagnetic layer and cobalt and boron as the free layer, and we follow the recipe that we learned earlier. So, we apply certain magnetic field, heat, anneal the material over a temperature which is more than the anneal temperature, let us say. Then after we cool down, we will have unidirectional anisotropy, which means the magnetization will be always at one particular direction in the absence of any magnetic field. Okay. If you apply high magnetic field, you may be able to switch, but once you remove the magnetic field, you will always end up here. Okay. So, this is the concept we used in the GMR sensor, and we use the same concept in plane MRAM also. Okay, so why we need to do pinning? Why don't we just have a layer without pinning? So, that is explained in this picture. So, we are talking about field assisted switching. Okay. So, in field assisted switching, we learnt that we will apply two magnetic fields, right, one along the easy direction, one magnetic field along the hard direction. So, by applying two magnetic fields, we select the MRAM that we want to switch, right. So, this means that the MRAM or the MTJ you make should have an easy and hard direction. So, it should have easy and hard directions. Okay, let's take this plane. Okay, so the magnetization is along this plane. Okay, so how many directions are possible for this magnetization to be along this plane? 360 degree. Okay, so the magnetization easy axis can be in any direction. So the easy direction can be 0, 90, or any angle between 0 and 360. Okay. So, in the case of in plane magnetization, the easy direction can be anywhere between 0 to 360 degree, but in that case we cannot know where is the easy direction or hard direction. Let us say you have wires like this, and we think that this should be the easy direction, this should be the hard direction, but if the MRAM below has in easy direction in any angle, we may not be able to switch the MRAM. Okay. So, to define the easy axis and hard axis, there are two possibilities. Okay. So, one possibility is you can use shape anisotropy. Okay. So, if you make elliptical bits, so you can say that easy axis are along this direction. So, this is the hard direction. So, this is one possibility. We can use elliptical bits. Okay, elliptical bits have shape anisotropy, but the problem is the area occupied by elliptical bits will be larger, right. Let us say this is the minimum feature that you can achieve with let us say f is the minimum feature that you can achieve with a lithography technique. Okay. Then this, I mean the diameter on the other side is like 2f. Okay. So, the area of your elliptical bit is going to be larger. Okay. That means you cannot pack more bits in a given chip. So, we do not desire elliptical bits because they occupy more area. So, we want circular bits. So, as I mentioned, the circular bits can have easy direction anywhere. Okay. So, they do not have shape anisotropy. There is nothing to fix the magnetization direction of these bits along any particular direction. Okay. So, this is the reason we use the antiferromagnetic material and do the magnetic field annealing technique to induce magnetization in one particular direction. Okay. So, let us say we deposit the ferromagnetic material on top of antiferromagnetic material and we apply a magnetic field along a particular direction. let us say in this case, okay, this is my wafer. During the annealing process, my magnetic field is along this direction. Okay, I cool down. So, after I cool down, all these small cells that you have, they will have easy direction along this direction. So you can set the easy direction by doing the field annealing process. So, this way you can have circular bits with easy direction all along one particular direction. Okay. So, that is why we need the AFM antiferromagnetic material in plane MRAM. Okay. Yeah. Okay. Why do we use high temperature for? I mean, we are operating MRAM devices at room temperature. So, the pinning should happen at room temperature. So, low temperature pinning is useless. So, we want to have pinning at room temperature or the operating temperature of MRAM, that is one thing, but we are annealing at high temperature to achieve the pinning effect, right. So, the annealing at high temperature is to ensure that you go above the anneal temperature. So, your antiferromagnetic material okay, to start with, your antiferromagnetic material itself may have domains. Okay. So, within this domain, let us say these are the anneal vectors. So, what happen if you zoom in here? So, that region, the magnetization of the neighboring spins of antiferromagnetic material will be antiparallel. So, all this will be there. Okay. So, during the annealing process, what you do, you apply a high temperature more than the anneal temperature. So, thereby you make the antiferromagnetic material to be a paramagnet. So, at this point of time, you apply certain magnetic field. So, this magnetic field is forcing the magnetization of the ferromagnetic layer on the top to be along certain direction. Okay, now you cool. Okay, now you cool the whole system, ferromagnetic antiferromagnetic layer sandwich. You cool down. So, when you cool down, now you may not have these domains. Okay, all the antiferromagnetic spins will be, I mean at the top they will be aligned with this magnetization. Like this. Okay. So, you need to heat at a temperature above Néel temperature. Okay. So, I mean quite often researchers do not bother about temperature. So, they say they observe some phenomena at 30 Kelvin. 30 Kelvin phenomena is useless for technology. So, when we are talking about technology, so we should be constrained to work on the limitations set by the industry. Okay. So, whether you make say some semiconductor chip, the temperature during some process will go even as high as 300 degrees Celsius. So, whatever material you make should be able to withstand this temperature. Okay. So, if you have material that does not tolerate 300 degrees Celsius, that material is useless. Okay. So, you can publish paper, but if you want to use something for technology, you have to play the game according to the rules. Okay. So, there are many requirements. So, a material design has to meet all the requirement. Okay. So, making a product is not easy. Okay. Doing research, you can do anything. You can observe some phenomena at 3 millikelvin and you say that it is very interesting. Okay. It is interesting, but it is useless. 3 millikelvin data is useless. Okay.
Thermal energy can also affect this.
Pardon?
Thermal energy can affect the spinning, right, in something if we come to around room temperature or something.
Thermal effects will affect. Yes, yes, we are going to learn that later. Okay, let's do the first question. So, the first question is okay. Yeah, I think, sorry. Oops. Okay, anyway, you scan using this one. Okay, let us go to question 1. So, question 1 is about how many layers are required in the case of an in-plane MRAM with an aspect ratio of 1. So, when you say aspect ratio, basically it is the length divided by length width ratio. Okay. So, aspect ratio 1 is basically like the length and width are same. Okay, many of you are wrong. Okay, MTJ requires how many layers? MTJ requires 3 layers, right? So, you need a reference layer, you need a magnesium oxide, you need a free layer. Okay, but we just learnt that if you are doing in plane MRAM, your magnetization can be at any angle within the plane. So, we need to define an easy direction. So, for that we need an AFM layer and the recipe that we need to pin the magnetization along certain direction. Okay. So, the correct answer is 4, not 3 or 2. I do not know who answered 3, 2. Okay. You really need to brush up whatever we have been learning so far. Okay. Sorry. Okay, correct answer is 4. Okay, next question. Okay, I am giving you some more time to give you, to give you time to answer correctly. Okay, many of you are wrong, like 14 of you are wrong. Okay, the correct answer is both. You should have chosen both. So, some of you have chosen both, I think. So, we are using an antiferromagnetic layer not just to fix the pin the magnetization direction, we are also using this to set the desired EZ axis. Okay, otherwise the magnetization is in random direction. Okay, majority of you are right. There is nothing stops us from using shape of the MRAM cells physics wise, but if you use shape, you have to use ellipse which occupies more area than a circle for a given diameter. Okay, so the correct answer is this one. Okay, so far we learned that we need at least 4 layers. So, antiferromagnetic layer, free layer, magnesium oxide reference layer. Okay, but we learned that if you have a reference layer like this, let us say this is your reference layer and this is your free layer. Let us say you magnetize the reference layer along certain direction. So, this is like north pole, south pole. So, you know that this will generate a magnetic field. Okay, so, this magnetic field can interfere with the free layer magnetization. Okay. So, if this is north pole, the free layer having this kind of magnetization is preferred than free layer having magnetization in this direction. Okay. So, anti-parallel direction is preferred than parallel direction. Okay. This we do not want. So, we do not want this free layer direction to be parallel or anti-parallel, not by this magnetic field, this should be decided by us. Okay. Suppose we want 1, we keep the magnetization to be anti-parallel. Suppose we want 0, we keep the magnetization to be parallel. Okay. We don't want this magnetic field to influence the magnetization direction of the free layer. Okay. So, to overcome that problem, people use the synthetic antiferromagnetic concept. Okay. So, 2 days ago I discussed this concept. So, if you have 2 ferromagnetic layers separated by a suitable thickness of ruthenium layer, so we learnt that the neighboring magnetization can point in antiparallel direction. So, this is the synthetic antiferromagnetic concept that we learnt a few days ago. Okay. So, when we have that synthetic antiferromagnetism set here with a ruthenium layer or iridium layer, now these 2 layers are antiparallel in direction, and you can notice that this is like north south. Okay. So, this is stable, the magnetization, I mean the magnetic field from this layer will go into this layer, the magnetic field from this side will go here. Okay. So, none of this field will go to the free layer. Now, you can notice that after we use the synthetic antiferromagnetic layer design, the stray field from the reference layer does not go to the free layer. Okay. So, it is just stuck within the reference layer itself. Okay. Now, free layer is free from stray magnetic field. Okay. So, for that reason the in plane MRAMs usually have this SAF design. Okay. So, now if you count the number of layers, so we have 1, 2, 3, 4, 5, 6 layers. So, previously we had like only 4 layers. I mean a simple MTJ has 3 layers. Okay. When you introduce pinning, we have 4 layers. When you introduce synthetic antiferromagnetic layers, now you have 6 layers. Okay. So, this is how the technology progresses. Okay. Then the second concept that we need to learn about the in plane MRAM is the thermal stability. Okay. So, a few days ago I taught you this thermal stability concept. So, we learned that KUV is the anisotropy that stabilizes the magnetization. So, that is the energy required for storing information, and if you make the volume of the entity that stores magnetization to be small, your KUV will be small, then the magnetization will not be stable. So, we learnt that the magnetization of the smaller units may flip as a function of time. This is not a video, I think, it is just a screenshot. So, in the video you notice that this magnetization was flipping as a function of time. So, it was pointing left sometime, pointing right sometime, and so on. Okay. So, this phenomenon happened in the magnetic recording. So, for in plane MRAM, usually we are using cobalt iron boron, which has a low anisotropy constant. So, the Ku itself is small. Okay. So, the volume cannot be much smaller. Okay. So, there is a limit to the volume. So, in the case of cobalt iron boron for in plane MRAM design, the diameter cannot be smaller than 60 nanometer. Okay. So, if you make the MRAM diameter smaller than 60 nanometer, your KUV becomes smaller, then KBT competes, then your magnetization starts fluctuating. Okay, you can do some calculation. For example, this is the anisotropy constant of cobalt iron boron. So, you know the Ku. Let us say you make 5 nanometer thick cobalt iron boron. You can calculate the diameter for this ratio. Okay. So, you want the KUV by KBT to be more than 60. So, this gives you 10 years of stability. Okay. So, once you write information, the information will be stable for 10 years if this ratio is more than 60. Okay. So, knowing the anisotropy constant, thickness, we can calculate what will be the diameter of the MRAM cell. Okay. So, if you substitute all these things, you will get the diameter to be 60 nanometer. Okay. So, what it means is that if you use cobalt iron boron with in plane magnetization for storing MRAM, you cannot achieve MRAMs below this diameter. So, this is the limit for in plane MRAM. So, that is one problem. Okay. So, problem of in plane MRAM, one problem is thermal stability. It limits to 60 nanometer. Okay, the second problem with the in plane MRAM is the writability. Okay. So, we know that magnetization is angular momentum, spin is angular momentum. So, let us say you have a spinning top. Okay. Spinning top is rotating like this. Okay. So, spinning top is rotating like this. So, its angular momentum is along this direction. Okay. So, when the spinning top is very fast, rapidly rotating, the angular momentum of the spinning top will be along this direction. But you would have noticed when the spinning top slows down, then this angular momentum is not in the perpendicular direction, it is like this. Okay. So, at some point of time when it slows down, the spinning top will go like this, then fall down, right. So, you would have noticed when you play with the spinning top, what is the word for spinning top in Hindi? Huh? Lettu. Okay. Okay. So, spinning top does same thing, right, like angular momentum is not coming down from this to this directly. So, it is like this, then slowly precesses, finally, the spinning top falls down. Okay. So, similar thing happens when you switch magnetization. Magnetization is an angular momentum. So, like the spinning top's angular momentum, magnetization also has angular momentum. So, if magnetization is pointing in this direction, so if you want to make magnetization to be in the opposite direction, again it has to be like precess, then finally switch to the other direction. Okay. So, this is the typical switching behavior. I mean, you cannot see this in VSM, in vibrating sample magnetometer or anything, you are measuring at a time scale of say few seconds. Okay. So, this precision, all these things happen in picoseconds, okay, hundreds of picoseconds. So, the magnetization goes from one direction to the other via precision. Okay. Now, let us take in plane MRAM. Let us say this is the initial magnetization direction. This is the final magnetization direction. So, during the switching, you see the path of magnetization. So, at one point of time magnetization is like this, then precesses, at some point of time it is precessing like this. Okay. So, this direction is perpendicular to the EZ direction. Okay. So, you see that the magnetization direction is perpendicular to the initial direction. Okay, so this point I should teach you something which I didn't teach you before. Okay, let us spend some time to learn some concepts before we come back here. So, let us go back to the Stoner-Wohlfarth switching, all those things. Let us say I have a piece of magnetic material, it has an easy direction and a hard direction. So, which of these two curves, okay, these are MH curves, right. So, which of these two curves is along easy direction, which is along the hard direction? Red is which direction? Red is along the easy direction and green is on hard direction, right. And what is this field? Huh? No, what was the term I used when I taught you the Stoner-Wohlfarth reversal mechanism? HK. Okay. So, we learnt that if you have a Stoner-Wohlfarth particle which has certain anisotropy direction, the easy and hard direction hysteresis loops will meet at this field called anisotropy field. Okay. So, this is something that we learnt, but there is something which I did not teach you before. Let us say we have a thin film, there is no other anisotropy, okay, no special anisotropy, I mean no other form of anisotropy. And this is a thin film. Okay, so, what makes the magnetization to be lying parallel to the film surface? Shape anisotropy, right. So, shape anisotropy will make the magnetization to be parallel to the in plane direction. Suppose I apply a magnetic field along this direction in the perpendicular direction. How much magnetic field that I need to make this magnetization to rotate in the perpendicular direction? Okay, initially the magnetization is parallel to this plane, but I apply magnetic field in the perpendicular direction. So, at some field it will come in the perpendicular direction. So, what is that field? I did not teach you, so you may not know, but you can guess. Okay, I did not teach you, so it is okay. So, the field you require to make this magnetization come out of this plane does not depend on any of these things. Okay. So, it is nothing to do with the HK, all those things, because we say that there is no special anisotropy except shape anisotropy. Okay. So, in this case the field you require to make the magnetization to be perpendicular is 4 pi m s. Okay. So, it does not depend on anything else like HK, all those things. So, this is only when we are talking about Stoner-Wohlforth mechanism, but in the absence of any other anisotropy, the field you require to make the magnetization perpendicular to the plane is only given by this formula. Okay. It is just proportional to m s. Okay. So, if your saturation magnetization is larger, then you need more magnetic field. If your saturation magnetization is smaller, you will need less magnetic field. So, for example, you take permalloy with a magnetization of 800 EMU per cc. Okay, permalloy will have magnetization in the plane, and if you want to make the permalloy loop in the perpendicular direction, so in the perpendicular direction permalloy loop will saturate at this field, which is 4 pi times 800 EMU per cc. So, that will be roughly around 10,000 Oersted. So, if you take say cobalt iron with a ms of 1200, so it will saturate at around 15,000 Oersted. Okay. So, this saturating field in the absence of any anisotropy depends only on this 4 pi ms. Okay, so, with this let us go to the next slide. But we can say that perpendicular direction is the hard axis. Yes, perpendicular direction is the hard direction. Yes. So, in this case it is the shape anisotropy that makes the magnetization in plane. This is not the same as HK. I mean, we do not use the word HK here. Okay, so, with that learning what we learned, let us come back here. So, you know that the magnetization is comfortable either pointing left or right or even in any direction within the plane, because the shape anisotropy makes the magnetization parallel to the film plane. But if you want to make the magnetization perpendicular to the plane, you have to spend a magnetic field. I mean, you have to apply magnetic field of the order of 4 pi ms, right. This is a huge energy. Okay. So, if you convert this magnetic field into energy, it will be a huge number. Okay. So, when you switch magnetization from right to left, what you are doing? So, quite often the magnetization is perpendicular to the plane. Okay. So, all this region you are spending more energy, more than the anisotropy energy that keeps the magnetization stable. Okay. So, that is what I have written here. So, the energy barrier that retains the information is 60 times kBt, but when you do the reversal process, the magnetization spends long time in the hard direction. Okay. So, the energy required to reverse the magnetization is like 6000 kBt. Okay. So, it is more 100 times more than the energy that keeps the magnetization stable. Okay. So, this is the problem. So, when you want to write in plane MRAM, you are spending too much energy, the energy much more than the energy barrier to write information. So, this is the second problem. So, first problem is thermal stability, which limits the diameter to be more than 60 nanometer. The second problem with the in plane MRAM is that you spend too much energy to write bits. So, we spend too much energy in writing information. So, there are some formula, but you do not need to worry about this formula. So, but you will notice that all this formula includes the 4 pi m that I described before. So, this H p also is same for pi m s. So, if you look at many papers related to MRAM, you will find either the critical current required to write information or some voltage required to write information, and in all of them you will find this term 4 pi m s. Okay. So, you need to spend more energy to write information. Okay, so, let us do some question and we can take a break. Okay, majority of you are wrong. Okay. You are wrong because you thought this is the right answer. This is not right answer. We are using an antiferromagnetic materials. We are using an antiferromagnetic material like iridium manganese to pin the magnetization direction. Okay, but oops, sorry. So, synthetic antiferromagnetic structure does not pin the magnetization direction. Okay. So, what synthetic antiferromagnetism does is it makes the two layers to be anti-parallel. Okay. So, synthetic antiferromagnetism only make the two layer magnetization to be anti-parallel. So, the two magnetization can be like this or like this. So, it can be in any direction. It does not pin in any particular direction. Pinning happens only with antiferromagnetic materials. Okay. So, we are using this only for reducing the stray magnetic field. So, 2 is the correct answer, only 4 of you are right. So, synthetic antiferromagnetism is different from the antiferromagnetism and exchange bias concept that we learned. Okay. So, be clear. So, this kind of question helps me to understand whether you are following correctly or not. So, we can recalibrate our knowledge by going through such question. Okay. So, antiferromagnetism is helping us to pin the magnetization direction. So, this is the one that helps. Okay. So, I hope you remember we are using antiferromagnetic material to pin the magnetization along particular direction. So, these materials are iridium, manganese, iron, manganese and things like that. Okay. So, when we are talking about synthetic antiferromagnetism, we are talking about two ferromagnetic layers like cobalt and boron separated by some material like ruthenium, iridium and things like that. So, this is synthetic antiferromagnetism. So, this is a material, this is a natural material. This is a synthesized material. Okay. So, you should know the difference. Secondly, this synthetic antiferromagnetism only ensures that the magnetization is anti-parallel. Okay. So, if I view from top, let us say we have several magnetic units which are in synthetic antiferromagnetic shape. So, from top they may be in any direction. Okay. So, if the top magnetization is pointing in one particular direction, the bottom will be anti-parallel to that. Okay. So, what synthetic antiferromagnetism does is only this. Okay. It will make the top and bottom to be anti-parallel to each other, but it cannot help in pinning this magnetization to be any particular direction. Okay. So, for pinning you need this concept and the magnetic field annealing. Okay, next question. Okay, again a majority of you are wrong. Okay. I don't know, is it tough to follow? Okay, the energy barrier of in plane MRAM. I told you that we design the energy barrier to be roughly 60 kBT. So, the KUV is roughly 60 kBT, but I told you that when we try to write information, the magnetization is going through precision, and the precision, there is a lot of time spent with magnetization in the perpendicular direction, and because of that I told you that the energy we require for writing information in the in plane MRAM technology is 6000 kBT. Okay, so, this is the energy barrier, and when you talk about this energy required to write information, it becomes larger than the energy barrier height because of the 4 pi ms term here. Okay, because the magnetization is like processing the direction, the hard direction, right. So, it is this one that causes the writability problem. Okay. So, if ms is large, this energy will be even larger. If ms is small, this energy may be a bit large, a bit small. So, it is basically the saturation magnetization that causes the writability problem. Okay, so the YouTube streaming videos are available. So maybe after you go home at night, you can watch the videos again to reinforce the concepts. Okay. So the next one is the perpendicular MRAM. So we'll cover this after a break. Okay, we'll go for tea.